Why is supercomputer cooling a massive engineering challenge? Imagine a machine so powerful it can perform millions of calculations every second. Now picture that same machine generating an enormous amount of heat in a tiny space. That's what supercomputers do, and keeping them cool is no simple task. When supercomputers run at full speed, they produce heat densities that are staggering. The processors and components are packed tightly together, so heat builds up quickly in small areas. Without proper cooling, these hotspots can cause hardware to overheat and break down. Traditional cooling methods like air cooling just don't cut it anymore. Air has low thermal conductivity, meaning it doesn't transfer heat efficiently. Water cooling is more effective because water can absorb and carry away heat faster. But even water cooling has its limits. It can lead to problems like water evaporation, chemical treatment needs, and complex plumbing systems. These systems are expensive to install and maintain, often costing millions of dollars and requiring months of planning. Energy consumption is another big challenge. Cooling systems can use nearly as much energy as the supercomputers themselves. This creates a cycle where more power is needed to keep the machines cool, which raises operational costs and environmental concerns. In warmer climates, cooling becomes even harder because the surrounding air is already hot, making heat rejection to the environment more difficult and costly. Managing heat is complicated because supercomputers don't run at a steady pace. When computational loads fluctuate, so does heat output. Designing cooling systems that can adapt quickly without wasting energy or risking overheating is a major engineering puzzle. New cooling technologies like liquid refrigerant systems and immersion cooling are promising. These methods involve submerging components in coolants or using phase change refrigerants that transfer heat efficiently without water loss. But they require precise control, special materials, and new infrastructure, making their design complex. The entire facility plays a role too. Cooling towers, pumps, heat exchangers, and building design all impact how well heat is removed. Maintaining these systems involves regular water treatment, equipment checks, and upgrades, adding to the complexity and costs. As supercomputers grow more powerful, their heat output increases, pushing current cooling methods to their limits. Engineers need advanced tools and research to develop new solutions that can handle future demands. Designing cooling systems for supercomputers is a balancing act. It involves managing heat transfer efficiently, reducing energy use, and ensuring reliability, all while keeping costs in check. Innovations like liquid cooling, immersion techniques, and smarter scheduling of heavy tasks during cooler times are some ways engineers are tackling these challenges. Ultimately, it's a complex puzzle that combines principles of heat transfer, fluid mechanics, thermodynamics, and facility engineering. It's what makes cooling supercomputers one of the most demanding engineering challenges today.